Hello everyone, this is Professor Keen. We are starting to work on Chapter 3 of A Student's Guide to the Great Physics texts. This chapter is called Conservation of Electrical Charge. In the past few lectures, we've been talking about the work of William Gilbert, the English philosopher and scientist who worked primarily on the study of magnetism. Now what we're going to do is turn our attention to electricity. We're going to focus on the work of Benjamin Franklin. And just as whenever you begin studying something, you've got to hop in somewhere. So there's a conversation going on about what is the nature of electricity. So before we start looking at Benjamin Franklin's correspondences, letters, experiments, and observations on electricity, it's probably worthwhile setting some historical context to better understand the work of Benjamin Franklin, who played a pivotal role in understanding electricity. So I'm going to be looking at the introductory comments in my text, and I'm going to be just probably reading some of these off for you because it provides a nice summary of the context. So here we go. Magnetism, though mysterious, was in fact far simpler to systematically study than electricity. This is largely due to the more permanent character of magnetism. For example, a piece of iron, once you magnetize it, is fairly immune to being demagnetized. This is something Gilbert spent considerable time talking about. Once you magnetize iron, it seems to stay that way for quite some time unless you heat it up above the Curie temperature or if you smash it with a hammer. On the other hand, electricity is a far more ephemeral or transient phenomenon. A piece of amber electrified by friction, that is by rubbing amber, it retains its electrification for a very short time, especially in humid weather conditions, or if you don't properly insulate it. This really made electrical effects very difficult to reproduce and to study in a systematic way. So it's no surprise then that the science of magnetism, at least in early times, proceeded much more rapidly than the science of electricity. It really wasn't until the 18th century and the development of techniques to carefully produce consistent amounts of electricity that the science of electricity began to proceed much more rapidly. We'll talk in a few moments about the development of what was called the frictional machine by Otto von Guericke, who also spent considerable time studying making a device that would create a vacuum. So let's turn now to one of the most famous researchers of electricity, Benjamin Franklin. He lived between 1706 and 1790. He was born in Boston, Massachusetts, a very famous American. He was one of 10 children. He became a printer's apprentice at the age of 12 years old, and then he moved to Philadelphia as a young man, where he acquired considerable wealth as the printer and editor of the widely read Pennsylvania Gazette and Poor Richard's Almanac. He was an avid reader since he was young, and Franklin conceived of and founded the first subscription library. You might think about this kind of like a private athletic club where you pay your fees, then you can go and lift weights. Think about a library operating in the same way. You pay fees, you can go in and check out books. He also founded Philadelphia's first fire department, which operated on a similar principle, the colony's first hospital and postal service, the American Philosophical Society, and the Academy and College of Philadelphia. That would later become the University of Pennsylvania. Through his activities as a writer and an entrepreneur, Franklin had great influence on civic life for many years. But his formal political career, which you've probably heard most about, really began when he was elected to the Pennsylvania House in 1751. Franklin was an outspoken critic of British policies at the time, such as exporting convicted felons to the American colonies. You may have heard about this in your American history courses. And Franklin went on to play a pivotal role in the American Revolution as a propagandist for the cause of the states, a political strategist, and a foreign diplomat, particularly to France. In 1776, he and 4 others were appointed by the Second Continental Congress to draft the Declaration of Independence, which would sever the American states from the British Empire. As he has a friend named Peter Collins that he has significant correspondence with, and as indicated in his first letter to his friend, Mr. Peter Collinson, which is included, we'll talk about this in a few minutes, Franklin devoted much of his leisure time to the careful study of natural philosophy, the philosophy of nature, science more broadly understood, especially the new science of electricity, which fascinated him. He mentions that he wants to think about little else in one of his early letters. It was this work, which was begun when he was 40 years old, that brought him fame in continental Europe. It had been known since ancient times that a small mass of amber, remember amber is petrified or solidified resin from a tree, often it washes up on a shore. Amber, when stroked, it would weakly attract little bits of paper or chaff to it. In fact, the Greek word for amber is electron, from which our word electricity is derived. And Franklin points out, by the way, in one of his texts, that calling it electricity is kind of like calling it ambricity, or tendency to behave like amber does. Remember, William Gilbert recognized in about 1600 that electrical forces on the one hand and magnetic forces on the other hand were fundamentally different. Since magnets don't need to be rubbed in order to produce their forces. You don't take a piece of magnet and rub it in order to make it magnetic. Some things are just born that way. When you mine lodestone out of the earth, it is simply magnetic. Subsequent research had revealed that different substances, when rubbed, could sometimes even exhibit subtle repulsive forces. Moreover, such frictionally induced electrical forces could in fact be amplified. A few decades before Franklin's birth, a man named Otto von Guericke had invented what he called a frictional machine. What this was, it was a sulfur globe about the size of a child's head, is how Franklin reports it, that would crackle and spark and attract little fragments of all sorts of metal and chaff when you get it spinning quickly and rub it with your dry hands. Immediately before Franklin began his own electrical researches, Otto von Guericke's frictional machine had been used at the University of Leiden to electrify what they called Muschenbroek's wonderful bottle. There was a scientist named Muschenbroek who developed it in Leiden in the Netherlands. This is also then called the Leyden jar. We'll spend some time talking about it because Franklin is fascinated by the Leyden jar. What is the Leyden jar? It's a round glass water-filled flask with a thin metal wire that sticks out through a cork on the top. This Leyden jar could store electricity, and it could also deliver a terrible shock, like a stroke of lightning, the researchers report, to unsuspecting experimenters who approach its protruding metal wire. It's delightful to read some of the accounts of Muschenbroek's bottle from these laboratories where they were playing probably practical jokes on each other and shocking each other. Anyhow, all of these wonderful electrical phenomena inspired a lot of speculation regarding their nature and their cause. By 1734, there was a French scientist named Charles-François de Cisternay-Dufay that he supposed that electrical phenomena can be attributed to the behavior of two distinct and invisible fluids. So there's these invisible fluids filling things that accounted for this electrical phenomena. That's the idea of Dufay. And these two fluids were called, on the one hand, vitreous electricity, which is produced by rubbing substances like glass and gemstones. That's why it's called vitreous electricity. And on the other hand, resinous electricity, which is produced by substances such as amber and hard resin rods and PVC pipes and other plastics when you rub them. So you have vitreous electricity and resinous electricity. And according to Dufay, each of these two invisible fluids repelled the same kind of fluid and attracted the opposite kind of fluid. So it's in this historical context that Franklin begins his famous experiments and observations on electricity. As mentioned at the outset of his first letter to Mr. Collinson, Franklin had just received, he says, an electrical tube in the mail with which to carry out his very own experimental researches. By rubbing this glass tube with leather or silk and then drawing a knuckle along the tube, one could readily collect what he called the electrical fire from the tube. When exploring this text below that we're going to be looking at, I want you to try to put yourself in Franklin's shoes, so to speak. That is, try to imagine that you yourself are approaching electricity for the very first time. Is it conceivable that electricity is, in fact, some kind of fluid? What experiments does Franklin perform, and what conclusions does he draw from these experiments? And I want you to think specifically, does he in fact adopt Dufay's two-fluid theory of electricity, or something slightly different? Finally, is Franklin correct? How do you know? All right, so now let's begin to look at the letters of Benjamin Franklin. Let's first look at this extract of letter 1 of Benjamin Franklin, which I am highlighting here. You'll notice in this letter what Franklin is doing is thanking Mr. Collinson for sending him this electrical tube that he's able to use to carry out his studies of electricity. What does this consist of? Well, it consists of a glass tube. You might think about it like this. I'll make a sketch. And then you could take this glass tube and rub it with a piece of silk or leather, for example. And when you rubbed it with silk or leather, here's glass. So you rub it, and when you do that, you produce electrification. He's going to explain what he does with this glass tube, and he's able to touch it to things and electrify them. He mentions in this text that these studies that he's carrying out really engrossed his attention, and little else interests him during his time of doing these studies. Okay, let's go on to letter number 2, which begins down here. And let's jump to the next page. So Franklin mentions in this letter that electricity, when you're studying it, he notices two specific phenomena. One is that electrified bodies are able to, pointed bodies, he says, are able to draw off and to throw off this electrical fire. So let's talk about some of the specific experiments he carries out in order to demonstrate how a pointed object is able to draw off or throw off electrical fire. Now, what does he mean, first of all, by electrical fire? He's assuming that when you electrify an object, it contains within itself some electrical fire, some tendency to spark. After all, how do we know things are electrified? They tend to spark. So there must be some kind of electrical fluid or something, electrical fire within them that they're able to throw off. Okay, so what are some of the experiments he carries out? Well, let's look at his first experiment in this section. The first experiment is he mentions that if you take an iron shot, so here's an iron sphere, he calls it a shot, and you place it atop a dry glass jar, so the neck of a glass jar. It's important that this glass jar is dry so that it does not leak off the electrification that you place on it. And suppose you rub this glass rod right here with the silk, and then you touch it to this iron shot. He says it becomes electrified. How does he know it becomes electrified? Well, because if you take a small silk thread and you hang from it a cork sphere. And he mentions that if you do this and you rest the cork sphere against the iron shot, and then if you rub the glass and touch the glass with the iron shot, suddenly the ball is repelled. It swings sideways by about 4 or 5 inches. So this iron shot has somehow become electrified in a way that repels this cork sphere. And now he's interested in this drawing off of electrical fire. What does he mean by this? Well, he says if you take a sharp bodkin, which apparently is like a long needle that one would put in their hair to hold their hair up, if you take a sharp bodkin, he says, and aim it at the iron shot while it's electrified and hold it perhaps 6 or 8 inches away, you'll see that as you do that, the cork sphere falls back toward the iron shot. So somehow this pointed needle is able to draw off or pull away the electrical fire that is within this iron shot so as to diminish the effect of repulsion. He says also that if you take a blunt body rather than a sharp body like a bodkin, you take a blunt body and bring it near the iron shot, it's much less effective at drawing off this electrical fire. In fact, you have to bring it within about 1 inch of the iron shot in order for the cork sphere to fall back toward the iron shot. So he concludes that sharp objects draw off this electrical fire, but only if those sharp objects are not insulated. So he talks about an experiment where he takes this bodkin and he embeds it in a wax rod, holds the wax rod and points it at the iron shot after it's been electrified, and it's less effective, and in fact I think he says it's ineffective in drawing off the electrical fire because the cork sphere stays repelled. But on the other hand, if you move your finger up and touch the iron part of the bodkin with your finger so it bypasses the wax, then it is able to draw off this electrical fire. So you need to have some kind of connection, it seems like, between the wire, your finger, and the ground, presumably, in order to draw off this electrical fire. He says you can draw off the electrical fire with a sharp wooden stick, but only if the wooden stick is wet. If you have a dry wooden stick aimed at the iron shot, it will not draw off the electrical fire. And by the way, what influences him in this case of talking about drawing off electrical fire? He says if you do this in the dark and you bring this sharp iron needle close to the iron shot and you look at it, as the cork is swinging back down, as it's losing its electricity, there's a small glow, a fire-like glow at the tip of this bodkin. So that's where this inspiration for this notion of an electrical fire within the iron shot comes from. All right, let's pause there and we'll come back to this in the next lecture.